Okay, welcome to the week 3 onboarding about test equipment. So one of the most basic pieces of equipment that you need to test a board is a DC power supply. They have two modes of operation and they'll automatically switch between them, and that's constant voltage or constant current. You set limits on the voltage and current that it is allowed to output, and then it will stop at whichever limit is hit first. So you can set a voltage limit. Most of our boards are powered by 12 volts. So if you set a 12 volt limit, then it'll output power until there's 12 volts at the output terminals. But the other thing you'd want to set is a current limit, because otherwise, if there's a short circuit, then without a current limit, then it would just draw a lot of power, and then the place where there is a short circuit would heat up and cause damage. So most of our boards having a 100 milliamp current limit would be more than enough, and this just makes sure that if there is a short circuit, then it won't heat up and won't draw a lot of power. So there's usually 3 output terminals. Red, like a red terminal usually indicates the positive output terminal. Black is usually the negative output terminal. And then there's sometimes a ground terminal, sometimes there isn't. And it's usually green, but I've also seen yellow. This image is showing a power supply. I believe we have this exact model in our bay, but we might just have a similar one. I don't know for sure. The way you'd use it is that there's a power button in the bottom left corner. So that's used to turn the power supply on. And then this one actually has multiple channels. So there's one channel that's dedicated to less than 6 volt operation. And then there's another one for plus or minus 25 volts. You can select the channel using these buttons up here in the top left here. And then there's another button to display the limits. So if you press that, it'll show you what the current voltage and current limits are set at. And then on the right side, there's an adjustment panel. You can turn this knob to either increase or decrease the limit. You can use these arrows to change the precision of the number that you're changing. And you can press the voltage or current button to switch between the voltage limit and the current limit. And then in the bottom right here, there's a output on-off button. So this will actually turn on the output at the terminals or turn it off. So yeah, I think that's pretty much everything. That's the basics of using a DC power supply anyways. Another useful tool is a digital multimeter, or DMM. Shown in this image is a handheld version. There's also benchtop versions that are larger and they're usually more precise and have higher voltage and current ratings. So it's pretty simple. This just measures voltage, current, and resistance, and a few other things as well. So some of the useful features are continuity check and diode polarity. So basically the way that you use is that there's this dial in the middle that you can turn to whichever setting you want to use. It's hard to see, but it's actually in the off position right now. But then anything that has a V just means voltage, and this one has a wavy line above it. That just means that it's alternating voltage, or AC. This one has a straight line and a dash line, which just means DC. This one says millivolts, so that's just for very small voltages. The omega is for resistance. These series of lines are supposed to represent sound waves, I guess. So that's the continuity mode, and when you set it in that mode, it will make a sound whenever there's a short circuit between the probes. The symbol of a diode is the diode polarity checking one, and it will either display something on the screen or make a noise, depending on the polarity of the diode that's connected between the terminals. You can also use this feature to check if if a BJT is working properly. And then A is for current. Again, there's AC and DC. There's also these symbols in yellow on the outside. And you select these features by turning the dial to that setting and then pressing the yellow button. Most other DMMs, it might not be a yellow button, but there'll be some button that lets you access the secondary functions. Most of them aren't too useful, but sometimes you might want to measure the capacitance of something. So there's a capacitor feature here. When you're connecting the probes, there's a black terminal called the common terminal that you would put the black probe to in. And then you can connect the red probe to either one of the red terminals, but it depends what you're trying to measure. So this one has a symbol, has a V for voltage, omega for resistance, continuity, capacitor, and diode checking features on this side. And there's a limit, so each DMM will have a limit of the rated voltage that it can withstand. So this is 600 volts between the common terminal and this terminal. The other terminal is used for current measurements. And this one has a 10 amp fuse in this DMM. So when you're making voltage measurements, you need to put the probes in parallel to whatever component you're measuring the voltage across. This is just directly from Kirchhoff's laws. And in order to get an accurate voltage measurement, the DMM needs to have a high impedance so that the current that it draws will be insignificant and won't change the operation of the circuit. Similarly, for current measurements, back to Kirchhoff's laws, the probe needs to be in series with the circuit in order to actually measure the same current that's flowing through the circuit. And in order to not impact the operation of the circuit, it needs to have a very low impedance so that the voltage drop across is very low, and then the current through the rest of the circuit doesn't change. So that's why the current sensing terminal is fused. So that's just to prevent if you accidentally connect the current probe across like a component that has a voltage, like in parallel to a voltage source. Because if you did that, then the low impedance of the probe would short circuit and you would draw a very large amount of current, which could damage the DMM. So it's fused to prevent that from happening. Also, if you are using a DMM and it's not, the current sensing feature isn't working, it might be because the fuse has been blown, so you might need to change that. Another type of multimeter is an LCR meter, and this is specifically designed to measure inductance, capacitance, and resistance. And it will tell you other features as well about the components, like the equivalent series resistance or the dissipation factor. But this is less commonly used, so I'm not going to focus on that. So electronic loads or sometimes called E-loads, just have two terminals and they just draw current depending on the mode that has been set. So there's 4 modes: constant current mode, so you just tell it how much current to draw and it'll draw that current. Constant voltage mode, it will draw current until the voltage at its terminals is equal to the voltage that's set. Constant power, it will just draw power until the voltage across its terminals times the current that it's drawing is set to the certain threshold. And then constant resistance, this basically just acts like a programmable resistor. So you can use Ohm's law to determine how much power or how much current and voltage it will draw. It's pretty simple to use. There's a power switch on the left side, and then you can select the mode using these buttons in the middle, and then you can change whatever the value you want to set it to using this dial, or you can just enter in the numpad. And then you can just connect your circuit to the 2 terminals here, and then there's an on-off button to actually tell it to start drawing power or not. Logic analyzers are very useful for analyzing digital signals. They're basically just a bunch of channels that have voltage comparators that will make a comparison and then store that in memory. And then you would usually connect it to a computer sign that has a program that displays the waveforms like this. On the right side, this is just what a typical logical analyzer would look like. It's just a small device that has has pins to connect jumper wires to your circuit, and then there's usually a USB cable to connect it to a computer. They typically have like eight channels, I think, but some of them will have more, like 16. And yeah, there's usually decoders built into the software. So this is an example from troubleshooting the AFE boards recently. So this is just showing like a successful SPI communication. These are just the SPI signals, and then the master sends out a clock, and then the master sends out a command on Mosey, and then Meso, the slave, responds. And then all that gets decoded in the bottom. So this is a very straightforward decoder that's just translating the high-low signals to a hexadecimal value. But you can also program your own decoders. So if you're working with a particular IC, you can make a decoder that will decode the hexadecimal values into the actual commands that are being sent. And then oscilloscopes are probably one of the more complicated piece of equipment that you'll commonly use. This is similar to a logic analyzer, but instead of just making a voltage comparison, this is actually like an analog voltmeter, and it will take samples at regular intervals and store that in memory. So you can view like analog waveforms using an oscilloscope. They typically only have about 4 channels, I think is most common. And there's a little bit of signal processing that you can do on the oscilloscope. And then some of the main controls, all the waveforms can be shifted. So I guess the 2 axes are like the vertical axis is the voltage of each signal, and then the horizontal axis is time. So you can shift the waveforms left and right and up and down using these small knobs here. The section on the left, it all relates to the voltage of the waveforms, and the section in the middle here just relates to the horizontal time scale of the waveforms. These large knobs at the bottom can be used to change the scale. So if you look at the oscilloscope screen, you can see that there's little divisions in the background. And commonly the voltage scale or the time scale is expressed in the number of volts or the number of seconds per division. So you can change that using these larger knobs at the bottom here. So the way that an oscilloscope actually displays the waveforms is that it will make measurements at regular intervals, and then it will store this in a buffer. And then when a certain condition is met, it will display the entire buffer as a picture to be seen on the screen. And the condition is usually a trigger that you set. So the most basic trigger is that you would specify a voltage, and then an edge. I'll talk about it more later, but you can specify a basic trigger that when a certain condition is met, then it takes this image and displays it on the screen. And the trigger is all controlled on the right side. And then there's a few buttons at the top that also change the mode that the trigger operates in. I should mention this is the model of oscilloscope that we have in our bay. So that's just why I'm showing you this. It will be similar, but slightly different between different models of oscilloscopes. There's also a clear button here that will clear the display. So that can be useful at times just to reset it. There's 2 menus on each side that I'll talk about a little bit later. And then those can just be controlled by these blue buttons on the side. Oh, and there's also a power switch on the bottom left. So you press that to turn it on. Yeah, one more thing is that once you have an image, you can activate cursors using a button on there that's labeled cursors. And this will place 2 cursors on the waveforms, and you have to tell it which channel to place them on. But then there will be a little box that will tell you the voltage and time at each cursor position. and then it will automatically calculate the difference in voltage or the difference in time. And it will also automatically calculate the frequency between the, just by taking the inverse of the difference in time between the cursors. So if you measure like a sinusoidal waveform like this blue one here, you could put each cursor at a beginning of a cycle and at the end of a cycle, and then it'll tell you the frequency of that waveform. So I was just going to go a little more in depth about how to use an oscilloscope, because it is one of the more complicated piece of equipment that we have. So these are the probes that you would connect to each of the channels. Each probe has a ground clip and there's a probe tip that's inside this piece here. The ground clip just provides a reference voltage to measure the voltage against, and the point of using a ground clip is to provide a relatively low impedance path, or low inductance path, to make accurate measurements. There are other techniques to decrease the inductance further, but this setup will be sufficient for most measurements. So this thing on the end, like, you actually can't see the probe tip in this image. This is an accessory that it's like a plastic sheath that when you pull it towards the probe, there will be a little hook that extends out the end, and this is just makes it easier to clamp onto a wire or another component to actually make measurements without having to hold the probe in place. So this is just a basic circuit schematic showing the probe, the cable, and then the oscilloscope input. So basically on the oscilloscope input, there's a 1 megohm resistance usually, and then there's also a parasitic capacitance. The cable has a parasitic capacitance as well. And then the probe has, generally the probes will have the option to include a 9 megohm resistor here. And that's seen on the probe here, where there's this little red switch that you can slide back and forth. On the left side, it says 1x, and on the right side, it says 10x. And this is referring to the attenuation of the probe. So if you switch it to 10x, it will put this resistor in series with the measurement. And so this will attenuate the signal so that this basically forms a voltage divider here with the internal resistance of the oscilloscope. So this is a 1 to 10 attenuation, or sorry, 1 to 9 attenuation, or like 1/10. The voltage here would be 1/10 of the original voltage. The reason that you'd want to do this is that this will decrease the current that travels along this path, which will reduce the impact of the voltage measurement, because it will reduce the load on the circuit. So you'll get a measurement that's closer to the actual voltage that's in the circuit. You might want to use 1x mode if you're measuring very small voltages, because if you attenuate a very small voltage, then the noise in the system can dominate that, and then you'll lose the measurement. So in that case, you might want to switch back to 1x mode, but generally it's good to keep it in 10x mode. You also have to tell the oscilloscope that you're using a 1/10 attenuation on the probe, and it will automatically scale the voltage so that you don't have to do that manually. I think that's typically done on this right menu. So when you select one of the channel buttons, it'll give you options for specifying details about the probe, I believe, on this side. So the other thing to notice here is that there's an adjustable capacitor in parallel with the probe resistance, and this is to help compensate the probes. This is to make up for all the other parasitic capacitances in the probe and the cable and the oscilloscope. I'll talk about that on the next slide, but that capacitor can be adjusted by turning a screwdriver in this little hole here. There's a better image on the next slide. So there's also different probe coupling options. I believe this is also in that same probe setup menu that I was telling you about. So the two basic ones are AC coupling and DC coupling. AC coupling just means that alternating current will be displayed, and DC coupling just shows the signal with the DC component included. I think usually you just make a measurement with DC coupling. The other thing to know is that these are just passive probes. So if you're measuring very high frequency signals, you would need a higher quality probe with active amplifiers and things. So these will generally just be used for relatively low frequency applications. Okay, so the way to compensate a probe is that all oscilloscopes will have some sort of waveform generator, and this is usually set to a 1 kilohertz square wave. In this case, it's on the bottom right. So this isn't the exact model of oscilloscope that we would have in our bay, but it's similar on ours. So it's still on the bottom right corner, and there's two, it's difficult to see because it's pointing towards the camera, but there's two metal terminals here. You would connect the probe like this, and then it's connected to channel 1. And you'll see some sort of waveform, when you turn on the oscilloscope, you'll see some sort of waveform shown. And you can take a screwdriver and adjust the capacitor inside the probe, and you should see the waveform changing like this. So you want to change it so that the wave is a square shape, because that shows that the probe is actually showing the proper original waveform. And again, the oscilloscope needs to be calibrated and properly outputting an actual square wave for this to actually be effective. Yeah, you should do this anytime that you're picking up like a new probe or changing probe from one channel to another, because going back to this image, like every channel will have a different parasitic capacitance or slightly different impedance, and same with the cable and same with the probe itself. So anytime you're using a new probe or a new accessory or a new channel, you should technically recompensate the probes. Although in most cases, it probably won't change your measurement that much, but if you want it to be accurate, you should do this. So yeah, to set up a trigger, the most basic trigger would be a simple voltage threshold, and then you can select an edge. So you can specify whether the waveform needs to be rising or falling, or you can also set it to either or. And then when the signal that is measuring meets that criteria, it will display it on the screen. You also can only select one channel for the threshold. And there's different modes as well. So if you set it to single, then it will, whenever it triggers, whenever the waveform triggers the criteria, then it will just display it once and then turn off the oscilloscope so it's not getting new images. Normal means that anytime the condition is met, it will just display a new image. Automatic will display the image if the condition is met, but if the condition is not met, then it will just display an image whenever the memory buffer is full. And rolling mode isn't actually related to the trigger, but it's sometimes included in the same settings. And rolling mode just means that it will just display whatever signal is being measured in real time. So it'll scroll from the right side of the screen to the left side of the screen. So just going back to the oscilloscope image here, there's a run and stop button here that will turn on the normal triggering mode. And then if you press it again, it'll turn off and stop collecting data. There's a single mode here, so you can press single and it will set up to trigger once. And then there's an auto button to start auto mode. And then there's a knob here that you can turn to adjust the voltage threshold. And I believe the edge that you trigger on will be specified in the right menu here. So there's also a lot of auto measurement features. So I mentioned before that you can use the cursors to make measurements, but there's also you can also set it up to automatically measure certain things. So if you just want to know the max or min of a waveform that you're measuring, you can set up an automatic measurement for that. You can also calculate the RMS or mean voltage. You can automatically calculate the peak-to-peak voltage of a waveform. You can find the frequency of a periodic waveform, the duty cycle, and then the rise and fall times. So those features would all be specified on the left side here. And then, yeah, like I said before, you'd use these blue buttons to select them. And you can apply different measurements to each channel. So it depends which channel is currently focused on. So in this case down here, you can see that channel number 1 is brighter than the other settings. So if you select any of these features, it will be measuring channel 1. If you want to measure a different channel, you'd have to actually press the channel buttons to select a different channel. And then you can apply the automatic measurements. So another thing that you don't need to worry about this too much, but just be aware of the fact that there's sometimes aliasing. So in these graphs, there's a line that's showing the signal, and then there's these dots that are showing the samples that the oscilloscope would take. So for these top two examples, you can see that the samples describe the original waveform very well. The bottom left image, it's a little bit harder to see the waveform, but it's still sufficient to describe it. And then as the frequency increases, and it's relatively high compared to the sampling rate, you can actually see that the samples look like a completely different waveform than the original wave. So just be aware that high frequency components may get distorted or may not look the same as what the actual signal is. And this is a function of the sampling rate of the oscilloscope and also the memory. So if you're looking at a large time scale, the oscilloscope will have a sampling rate that is the maximum value it can sample at. But if you're looking at a large time scale, it might be limited by the memory that it has. So it will actually automatically decrease the sampling rate in order to display a large time scale. And so when you're looking at a large time scale, you'll typically see that your waveforms will lose detail because it can't keep the sampling rate high enough to accurately measure the high frequency components. This is another kind of interesting mode that most oscilloscopes have, which is XY mode. So before I mentioned that the x-axis is the time, but you can actually change it so that the x-axis is another channel. And then you can plot one channel versus another channel. This is more useful for periodic functions. So the top left image here, this would show like two sine functions that are in phase. And it's just a straight line. But then as you increase the phase difference between them, you get more of this oval shape. And then if you increase it by pi over 2, then one of the functions would be a sine wave and the other one would be a cosine function. So that would just describe a circle. Similarly, if you change the frequency between the two signals, you'll get these other strange shapes. So this one just has like one of the channels has a frequency that is half the frequency of the other channel. These frequencies have a 2:3 ratio and these ones have 3:4 ratio. These are called Lissajous figures after the person who made these popular, I guess, as a method of analyzing periodic waveforms. So just for fun, one of the things you can do with this is make oscilloscope art, and it's typically done on CRT oscilloscopes just for the aesthetic of the lines and everything. But yeah, you can make pretty much any shape you want if you make a complex enough waveform on each channel. The last thing I want to talk about is that you can also apply math and operators on the waveforms that you're looking at. So if you measure the voltage at 2 points in a circuit, you can actually take the algebraic difference between them. And that can be useful for measuring currents, because you can take the voltage at 2 points across a resistor, and then you can use Ohm's law to find the current through that resistor. Yeah, I guess you'll notice that up until now, I've only talked about measuring voltages with oscilloscopes, and that's because current probes are very expensive. So typically, you're just measuring voltage with an oscilloscope. You can also apply a fast Fourier transform. So this will just convert the signal from time domain to frequency domain. You can see which harmonics are present in a signal. There's also logic functions, so and, or, XOR, and not. You can apply functions like integration, differentiation, and there's also filters like low pass filters and high pass filters you can apply. So an example of a case you might want to do that is that if you know you're measuring a low frequency signal, but your oscilloscope, if your oscilloscope is capable of measuring higher frequencies, then there might be noise included in the measurement. So if you apply a low pass filter, then it will eliminate all the high frequency noise and it won't interfere with your low frequency measurement. And here are some of the useful resources. So we have a Confluence page that has some information about the equipment that we have in the bay, and it also has the manuals for our equipment. So if you want to read more about the more advanced features of an oscilloscope or of any of the equipment I've talked about, you can look there. There's also other guides online about how to use oscilloscopes and other equipment. Are there any questions?
Thanks, Lee. That was like really detailed. That was great. I think there's like one question in the chat, and I'll just reiterate it for the recording. When do you use AC coupling? And you basically just want to look at AC coupling versus DC coupling when you want to take off that DC offset from your signal. So if you want to look at a waveform that's riding on a rail, the DC offset, maybe like 5 volts, 12 volts, AC mode will isolate that. And then Shanika asked another question. Shanika, sorry.
Aliasing it's not usually a problem, but if you want to measure a high frequency signal, for example, if you're measuring like a gigahertz clock signal, for example, you would need a very high quality oscilloscope that's actually capable of measuring that. Otherwise, you might see a signal that looks like the clock signal, but it'll be at a lower frequency than what it actually is. And yeah, to prevent it, you really just need either a higher quality oscilloscope, or sometimes you have the option of specifying how much memory is used for each capture. And again, each oscilloscope will have a maximum, but you might be able to increase the amount of memory available to it, or you can just decrease the time scale that you're looking at. But I wouldn't say it's usually a problem. You just need to be aware that if you're looking at a large time scale, you might not be actually seeing every clock cycle that's actually happening.
Any other questions? If not, cool. Thanks everyone. This is our third and second last onboarding for this term, and it'll be super useful